Swayam Prabha. Digital India. Educated India.
He will talk about the roles of process systems engineering in the fuel cell research and development. So please welcome Professor Kim.
Thank you very much for the kind introduction, Professor Kano. Actually, he's my PhD supervisor, co-supervisor, so I'm very happy to be introduced to him in this kind of... Anyway, I'm very happy to be here to give an invited lecture, and I would appreciate all the people, and especially Raj, or the organizer of this conference. So let's get started. Today, I'm going to talk about the role of the PSCs in fuel cell research and development. Fuel cell is a kind of new technology for the hydrogen usage. So, and the fuel cell systems is very sophisticated. So the integration or synthesis of the system is very important. So the PSC researchers are very expected to play a crucial role. So then today I will talk about the current situation of fuel cell R&D in Japan and the future expectation and what I am doing now. So let's think about firstly the strengths of PSC. As many researchers in this conference even told us many, but my opinion is that one of the most important strengths of PSC is that PSC researchers can do both analysis of decomposition and synthesis and aggregation. Like if we have some given system here, but if the details or granularity is low, then we can improve the resolution, and we have inside this system, then we can make subsystems if necessary, right? And in other words, PS researchers are very good at using or making many sizes of blocks and connect or integrate them to solve certain problem. That kind of philosophy is, I think, the most important strength of PSC. In this figure, also the represents the similar words, similar strengths. It is written in 1983, before I was born. And if we have given system here, we can decompose, or we can unify or synthesis bigger systems if necessary. That kind of the philosophy is very the feature of the PSC. And also the PSC methods have been applied, that kind of philosophy applied to many fields. Typically chemical and petrochemical engineering were the target application of PSC. And then the time passed, many application we have many application. For example, energy, biosystems, pharmaceutical, healthcare, social, and now we have the most important problem of carbon neutrality of SDGs. In sub-theme of the energy or that kind of carbon neutrality, fuel cell research are there. Especially, we have many kind of fuel cell, but today's talk focusing on only polymer electrode fuel cell. And what is fuel cell, or what's the needs for fuel cell? I will talk about this. Background, the demands for the carbon neutrality and hydrogen energy uses are increasing to achieve carbon neutrality. This table shows the policy provided by the many countries from these 5 years: Netherlands, USA, EU, Japan, Australia, and also Republic of Korea. Many countries declare that they will increase the usage of hydrogen. And many tons of the investment are now undergoing. In Japan, former Prime Minister Yoshihide Suga announced that Japan will achieve carbon neutrality by 2050. So in Japan, many investment or many national projects are undergoing to achieve this grand challenge. And so what is fuel cell? Very in simple way, it generates electricity and H2O, water, from hydrogen and oxygen. So if we use block diagram, which are very familiar to you, PhD researchers, and the inputs are O2 and H2. Then FC, I mean this single cell, generates the electricity and H2O. Today, I'm gonna decompose this FC single cell, and I'm gonna synthesize the FC system in total. Then I will talk about the role of the PSC. And also, this slide shows the feature of the FC and FC R&D. FC itself has two main features. One is multi-scale. This means that nanostructure inside a cell affect the system performance. Like here, we have the picture of catalyst. The orange one is a particle, platinum particle. It is catalyst, which size is like 1 or 2 nanometer. And this green line is meaning the ionomer, which conduct a proton from the anode side. And the structure of this catalyst layer affect the system performance. The system means, for example, car, or a generator, or a train, anything. That is one of the most important feature of FC. And also, to develop or to design the nice FC, we need many kinds of research knowledge subject, like transport phenomena, of course. Chemical reaction happens inside, and electrochemistry to understand the electrochemistry in the MEAs, and mechanical engineering also to design the machine, and also material engineering to characterize the catalyst, or to make better catalyst, or to make better materials for the nice car or something like that. And also control engineering or optimization method are totally required. So multidisciplinary feature is very important in FC R&D. Okay, then let's decompose or analyze the FC single cell. Here we have a blue box FC single cell, and inside the FC single cell, we have many components. And from top, we have anode side bipolar plate or channel. This conducts the electricity here, and also channel for the H2 transportation. And then H2 comes here from here, and then H2 goes to the anode gas diffusion layer. This is for the distribution of gas in the evenly distribute the anode catalyst layer. And in the anode catalyst layer, then the H2 reacts to the 2 proton, and here we have electricity. And then the proton goes through the PEM, proton exchange membrane, and then at the cathode layer, proton and oxygen and electricity meets. Then this reaction, the O2 and the hydrogen reacts, and then we have water here. From the cathode side, O2 comes in, and cathode bipolar plate and channel are there, and cathode gas diffusion layer diffuse or transport the O2 to the cathode catalyst layer. And electricity go outside of the FC single cell, and here we have a work, or here, and electricity go back to the cathode bipolar plate. So in the last slide, just I showed the O2 and H2 go to the FC, and then we can get electricity on the H2O. That's a bit too simple representation of the FC. inside FC, we have many components, and also we have many research themes for each part of these blocks. So here are the research questions for material engineers, typically for each part of the component of FC. For anode or cathode bipolar plate or channel, it is required to optimize shape for effective gas transfer with less pressure drop. It's very tough work, and some expert researchers are focusing on just this area. And also, anode cathode gas distribution layer, it is required that make a thinner layer to reduce the gas transfer resistance and ohm resistance without increasing concentration difference at catalyst layer. It's very difficult problem, of course, and some experts just focusing on this problem. And also, this is mainly very active research questions for anode and cathode catalyst layer. Many researchers want to make a highly active catalyst with high durability and less cost. But they don't know the system performance or controllability of the system. But there are many kind of research. And also for PEM, proton exchange membrane, they want to make a PEM with high thermal durability and proton conductivity even at low relative humidity. And other than these questions, there are many kinds of material engineering problems in fuel cell research and development. But the material engineer doesn't know the system performance, or don't even not very interested in the system performance. They just wanted to make new material engineering. That's a kind of loss. So for the PhD researchers, we request to integrate to this kind of knowledge to evaluate the system performance, or give a suggestion to the direction of the research to these kind of material engineering to facilitate the maximize the speed of the FC R&D. Okay, then let's synthesize the FC systems. An FC system, of course, are not simply the single cell. Of course, we need FC, many kind of FC, many numbers of FC, I mean. And we call FC stack, in which FC is accumulated or stacked. And of course, to give the air or oxygen to the FC stack, we need air compressor, right? And for A2, we need injector. And also, FC stack generates heat by the reaction. Then water pump is required to convey the coolant. And then we can have electricity, water, and purge gas is the output. So FC systems are composed of many kind of components. So we need synthesize nicely FC system by using these kind of components also, not only the FC single cell. Then of course, H2 tank over here, and radiator here, valves, many valves are there, are also needed. And also pipe, of course, needed. So this is green lines means air system. Here the air, the ambient air is compressed to the air compressor, and then air goes to the FC stack. In the FC stack, that kind of reaction happens. And after, the exhaust gas goes to the output, right? Then the red line means H2 system. Here, for the vehicle or generator, there must be a hydrogen tank. And from the hydrogen tank, the pressure regulator, we have 3 pressure regulators here, and they decrease the pressures, and we transfer the hydrogen to the FC anode, and then, or maybe there, the reaction happens. And after the reaction happens, then we have to recycle the FC system to improve the fuel economy. And sometimes the exhaust valve opens, then the exhaust gas goes to here. Also, here is a cooling system. We have water pump, and water goes into the FC stack to cool down the FC. And after the radiator, from the radiator, the heat was rejected to the ambient. So we need to design all the things to develop our FC system, right? That's the very tough work. And also, we need, of course, controller. I explained this part in the last slide here, FC plant. So to operate nicely the FC plant, we need FC plant controller, of course. And what is the set point? What is the control variables? In general, the net power have a set point, and set point of the net power is given to the FC plant controller. Then FC plant controller determines the valve angle or rotational speed of water pump, radiator fan, or ACP, air compressor, or H2 pump. Then these kind of manipulated variables are inputted to FC system. Then FC plant moves, and sometimes the electricity generates. And this kind of closed loop simulation or closed loop operation is required to implement the FC system in linearity. And of course, FC plant controller are also composed of many components. In this, we developed a model of a controller like this. Here, the set point of net power comes here, and electric power system controller determines the set point of FC stack current, because power is consists of the current and voltage of the cell. We just calculate the set point of FC stack current, and then FC stack controller determines the set point of FC stack state. And in this FC stack controller, H2 system, air system, cooling system controllers are inside to determine the very efficient way of using controllers determine the set point of FC stack state to use the FC system very efficient way. Then to realize the set point of FC stack state, the unit controller determines the valve angle or rotational speed, or such kind of variables are determined in this controller. So we need, again, the many components to realize the FC system. And for the systems engineer, research questions are like this. What size of compressor should we adopt? Or what size of H tank should we adopt? Or what is the optimal operation condition for maximizing the efficiency or minimizing the fuel cell H2 fuel consumption? Or what type of controller do you use? Or can we control the temperature inside the cell or stack even when the large amount of the power is required? If not, what size of radiator is needed? That kind of questions are given to the systems engineer. Do you feel that there is a huge gap between research questions for material engineers and system engineers? We are doing the same thing. We want to reduce the environmental impact or CO2 footprint, but in many researchers have many different research questions. So that means for each researchers, they don't know the total performance of the FC system. So we need to integrate this kind of information and or integrate the power of all the researchers to the one direction. Here, we have the expectation to PSE in FC R&D because many kind of researchers are doing the research on FC, but individual researchers are trying to just improve their material, their simulator, or their machine, their unit. But they do not know how much impact will be available when some change happens. For example, the nanostructure change, then what the performance of the car will be. To integrate the knowledge and maximize the speed of FC R&D, then PSE researchers are expected to play crucial roles. The strength of PSE analysis and synthesis is highly required. And then to bridge the gap between the questions for the material engineers and system engineers, now Japan have a national project for developing the high platform, the FCs. And we have 5 groups basically: materials informatics group, material analysis, simulation, and electrochemical evaluation, and management group. And basically we have 2 work packages. One is data-driven, and one is model-driven. I'm sorry. And in the data-driven approach, the many data are measured at very sophisticated, very expensive instrument like X-ray or something like that. Then all the data are planned into the big, huge database, and then the material AI expert will extract some knowledge from the database and will show the new possible way of making the materials or structured materials. That is kind of one thing. And also for the model-driven, we are developing the physical model for each scale of the fuel cell, from nano to the meter. And I belong to the simulation group and developing the physical model for simulating the FC system from atomic viewpoint to the meter or system viewpoint. Here is a member of the simulation group. The Professor Kawase is a leader of this simulation group, and the other 1, 2, 3, 4, 5, 6, 8, or 10 people are doing research, and one people corresponds to this one simulator, or one phenomena, or one scale. And we have been doing the research for making the good simulators for each scale of the fuel cell phenomena. And then this graph shows how much simulators or how much phenomena should be considered in PFC. It's very complicated, even for single cell. We need a model for roughly saying the PEM, and also the channel here, and GDL, gas diffusion layer, and also electrode model. And even for the fabrication process model is required because the nanostructure will be determined by how they are produced in the process. And for the PEM, we need PEM degradation model, and degradation model are composed of 3 phenomena: chemical one, mechanical one, and a mitigation of radical quencher, something like that. So we need some expert for just modeling this phenomenon, right? And then here PEM water sorption dynamics model, because the relative humidity or how wet in the fuel cell strongly affect the performance of the FC. So we need a model for the water behavior in the cell. And also, as I mentioned, GDL is for evenly distribute the gas into the FC. So we need a very sophisticated way of how the gas are distributed in the cell. the size of GDL is like, how can I say, 10 micrometer or something like that. Very thin, very small scale phenomena understanding is required. And also, the very similar to the GDL, the flow pattern for the channel is very important. And for the electrode, we need many. And one most important is catalyst activity model. Because electrochemical reaction is very slow in FC, so we need highly active catalyst. But we don't know what factor is dominant in catalyst layer, catalyst activity. But so we need a model for that one. And also this catalyst activity depends on the humidity. Then we need many measurement of many sophisticated way of modeling this catalyst activity. And other are, I don't like to go on detail, but many kind of phenomena or many kind of models are needed. And that's for the cell itself, single cell itself. And we need, of course, FC stack model or a cooling model, which will be the 3D model. And also FC system model, we need, as I mentioned, BOP, balance of plant, auxiliary systems. And of course, we need to apply these simulators to many kind of system like vehicle, the bus, the ship, or any kind of XG-based systems. We should have the simulator for many kind of systems. And to realize the total simulator, we just propose the synthesis of integrated simulator. For this, firstly, here is a macro simulator, which is called FC Dynamo. And this is a very most rough simulator, but it is very fast, and it can evaluate the system performance, like how many QL is required, how much is the efficiency or something like that. And from here, here is a Mesos simulator, which is a little bit sophisticated simulator. And this simulator can calculate how the gas is moving in the catalyst layer. And that kind of simulator gives the input of the macro scale simulator. Then, yeah, some kind of change in catalyst layer could be explained, could be evaluated by the macro scale simulator on the basis of the FC performance. And also, we have many kind of simulator, like here mesoscale simulator and here nanoscale simulator, which calculates the catalyst layer structure formation. And also here, we can input the materials information measured by the materials engineers. So in that meaning, we are totally connected. Material engineers and system performance are totally connected by using this kind of integrated simulator. Right? And today, because of the limited time, I will talk about just macro scale simulator and mesoscale simulator here. We developed the integrated XC system simulator like this. As I mentioned, XC system have many components. Okay? And here is the input, and here is the controller, and here is a virtual plant system, and here is output. We could realize the closed loop simulator. This is very comprehensive, fast, dynamic, accurate, user-friendly simulator. And physical models are inside here, integrated XC system, and it's very easy to modify. And this simulator, the accuracy of this simulator was validated by using the car produced by Toyota, validated by the car data measured in the car, and prototype vehicle were used, and additional sensor were implemented in the car, and many kind of variables are measured. And here is a validation result. The x-axis is time, and y-axis is the FC stack current, its concentration or liquid water level in the separator. And here is the FC performance. And red and blue experiment and model result. And it shows very good match in the between model and experiment. And also, okay, this at the June at the Kyoto PSE, we displayed the Mirai produced by the Toyota. And here is Dr. Grossman. Dr. Grossman rode on this car, and he said, "Oh, this car is very nice." And also that by using the macro scale simulator, some change in MEA could be evaluated. For example, if we need, we can make the GDL very thin, or if we can make PEM thickness very thin, in, for example, half, or if we have some nice catalyst whose activity is twice as usual, then the macro simulator can evaluate the system performance. Here is the H2 consumption. And then if we have 3 improvement, then by comparing these values, maybe the 10 or 8% of the fuel economy could be improved, or cell performance improved like this. Now, of course, it can be used for the control optimization. Here is the energy consumption of the BOP. And at the certain operation condition, air compressor has a dominant consumption of power. So to generate the power, we need the power for the ACP or something like that as a component. So to reduce this power, we developed a system for automatically change the controller setting. And for example, here we change the flow rate of O2 to the FC stack. And in a certain operation condition, the total performance or net efficiency could be reduced, could be increased by 4 or 1%. That's huge. Also, next I will introduce the integrated use of macro and mesoscale simulators here. Because the FC macro scale simulator has a limitation that the input of the FC macro scale simulator is limited. By using these simulators, we can take many kind of measurement from the material engineers. And in mesoscale simulation, many kind of sophisticated, detailed information on the catalyst in Toyota Mirai could be inputted. For example, the structure of catalyst layer, or pore structure, or PT particle size distribution, or size of carbon agglomerate. That's a real measurement from the material engineers. By using these inputs, the mesoscale simulator could calculate or could simulate the catalyst layer structure like this. And for these are for fresh catalyst, and these are for degraded catalyst. And by these results, then we can get the cell performance, and then parameter determination could be done for macro scale simulation. And here is a system performance result by using the degraded and fresh catalyst. Here we have the overheat for the high FC system net power, and poor tracking could be just done. And then here is the FC system H2 consumption amount, and if we use fresh catalyst, 5% of the H2 consumption could be reduced. Or in other words, degraded catalyst worsened the H2 consumption amount by 5%. To quantify this number is very important for material engineers. Also, I'd like to synthesize the FC around the platform, including the human. Firstly, this is a kind of closed loop activity of simulation. First, input about new materials from material researchers are inputted, for example, mesoscale simulator or whatever simulated. Then the mesoscale simulator can calculate the FC cell performance, which is interface of the meso and macro scale simulators. Then we can determine the parameter for macro scale simulators. And after that, by using the FC dynamo or macro scale simulator, then we can have dynamic system behaviors. Then the many kind of researchers, for example, simulation researchers and material researchers comes here. Or I write here Waigaya. This means Japanese the discussion in sometimes with drinking alcohol, and we can have discussion obtaining by the based on the dynamic system behavior, and after we can exchange the opinions from between the many kinds of researchers, and then I believe it would facilitate each work for the simulation researchers or material researchers. After Waigaya, then simulation researchers and material researchers go back to their position, and then they can start identically their work to improve, for example, material experiments, or simulation researchers can improve their own simulators based on the opinions here, or thought here. Okay, then summary. And here, today, I talked about the feature of the fuel cell and its research and development. Fuel cell has feature of multi-scale, multidiscipline. That's a very difficult one, but very interesting problem for us, for me at least, and I hope that interesting for you, PhD researchers. And also, I introduced the Japanese national project on FC platform. We are now developing the model from the molecule to the system and evaluated the system performance by the simulation by using the many kinds of newly developed materials. And also, we can do, of course, optimize the controllers and integrate use of the macro and mesoscale simulator, make the very high platform for everyone relating the FC R&D. And also the Japanese government also requires a PhD researcher are very encouraged to join FC field, since their strengths or your strengths are crucial to accelerate FC R&D. That's all, and thank you for the kind attention to me.
Thank you very much for a nice talk, Professor Kim. Now the session is open to for. Yes.
Hi, thank you. I'm Yogendra Shastri from IIT Bombay. So thanks for the talk. So I have a question. You have these different models at different scales. Are they connected in real time, or they are standalone and you have offline data transfer?
Yeah, not real time. We connect the simulators offline by using the data. Like here we have a data from the mesoscale simulation. Then the macro scale simulation was done after, because the calculation speed is totally different. This mesoscale simulator is very fast, 15 times faster, but this mesoscale simulator or nanoscale simulator even, it takes maybe 10 hours, or for nanoscale simulation, it takes 1 month or something like that. So I don't like to connect in real time.
Okay. Fine. Thanks.
Any other question or comment?
Thank you for your detailed presentation, Professor. In terms of the long operation of the FC, maybe I think there are some mechanical damage, including maybe a swelling effects of the membrane or some things. How could that long-term mechanical some damage could be considered in the overall framework that you presented in before, and if it's available, which simulators can be do that?
Yes, we are now developing also the model for degradation, including mechanical one and chemical one. So, and also the macro scale simulator is very fast, 50 times. So, I mean, when we calculate 1 week, then one years of the simulation could be done. Then we can evaluate how did each part are damaged.
So now the micro simulator could be simulate that part.
Not total. Firstly, the microscopic understanding is required to formulate the physics. Then I want to somehow merge the information to realize the fast calculation, which is done in macro scale simulation.
Okay, thank you.
Okay, I think now it's time to move on to the next presentation. So please join me to appreciate the presentation for Professor Kim.